And our penultimate session today is going to be on thermal treatment, thermal remediation of VOCs, SVOCs, and PFAS from Lauren Soos. Lauren is the Director of Market Solutions at TRS Group, where she collaborates with her clients and team members on thermal remediation solutions. Since 2003, she has worked in the environmental consulting and remediation industry, managing complex thermal remediation projects across the country. In 2009, Lauren implemented her first thermal project and has enjoyed working with these technologies since. She is a self-diagnosed geeky environmental engineer and lives in New Hampshire with her husband Seth and their daughters Emma and Ada, where she does all things outdoors, but mostly skiing. Perfect. And with that, thank you, Lauren. I think you're going to use this, right?
Yes, I'm hoping that I don't have to carry this around. Is that all right? Okay, Brant's giving me the thumbs up, so I'm going to go with that. And I'm a little paranoid about timing, so I will use a little stopwatch here just to try to keep things on track. So yeah, as Sheena mentions, all things thermal. Got obsessed with thermal around 2009 when I got to implement my first ever thermal remediation project, and have been doing it exclusively ever since. So yeah, I'm going to geek out, I guess, with you guys. Hopefully you guys end up liking thermal at the end of this. I'm curious, how many people have had the opportunity to implement thermal on one of their projects? Josh, I know you touched the project.
I mean, I sampled the thermal job, and there was a lot.
So no one else. Your company helped support some downgrading stuff, right? All right, so this is a lot of newbies, I guess. That's awesome. So some basics about thermal as I lose my timer here. Okay, let's go back to the beginning. So basics about thermal. We're back in the source area. So we were talking in the previous session about what to do outside of that source area, how to affect change, down gradient, before receptors. Right now we're going all the way back to the source area where we're going to be, focusing on in situ treatment again. We take care of a lot of thermal remediation practitioners, address a lot of DNAPL issues. So we'll be talking about DNAPL today quite a bit. Very effective technologies. There's a few different technologies that we'll discuss, but thermal technology is very effective with VOCs and essentially all different types of matrices. We were talking about, the differences in conductivity, hydraulic conductivity of some of that material. It doesn't really matter with thermal, whether it's rock or sand or clay, or the thermal vendors are very confident that they'll be able to heat it up. We'll talk about some of the data that drives decision-making with regards to what different kinds of thermal technologies will work, and how that impacts maybe some additional add-on systems to slow down water flow. But big picture wise, thermal vendor is very confident that they'll be able to heat up the matrix, whatever it is. When it comes to semi-volatiles and PFAS, which I do have a case study today talking about some work that we've done with PFAS, we are talking about applications in the vadose zone or ex situ applications. So high temperature stuff is where we're going with those contaminants. VOCs, we're just doing most of the work that we do in situ. So before we even start moving the soil around. With any of these thermal projects, making sure that we can capture the contaminant vapors, the steam that we're creating, the soil vapor is integral to the success of a project. So you've got to have a very confident vapor extraction system that gets deployed along with these thermal projects. Super fast operation side, of course, there's some upfront planning and then there's construction, but with regards to the operation of the system, even high temperature applications, it's all about delivering power quickly and getting that equipment to the site and then moving it on to the next one is the big focus for thermal vendors. So you see these projects happening really, really quickly with mass reductions that are 99.9999% reductions is typically the goal. On the left-hand side is a really small little dry cleaner project that we worked on, shopping center, downtown Alexandria. adorable little community right outside of DC. Back door of the dry cleaner where all the good PCE is disposed of. And we were heating right underneath the dry cleaner, underneath the basement, and a small area in the parking lot. The starting concentrations are right there in the background in groundwater wells. And then the data that's represented in the two bar graphs up front in the foreground is how we were able to make decisions that the system was to be shut down. Our goal at this particular project, this was a guaranteed project for our company. So our contractual goal was actually reaching 60 micrograms per liter in groundwater. That was the goal that we took on. So it represented 5 orders of reduction at that site. Moving on, the technology that we as thermal providers end up being compared to the most is dig and haul in the source area. So when you're looking for, we talked about the pace of these projects, a really fast removal of the source. Thermal is most often compared to like a excavation and offsite disposal scenario. There are many scenarios where dig and haul makes way more sense. When we start to look at waste that has like a hazardous waste listing, so really chlorinated solvent type of waste, and you're starting to talk about volumes that are around 2,000 cubic yards of material, that's really when it starts to make sense. Okay, let's take a look at a thermal remedy. What would that in situ application look like dollar value wise? But just keep in mind, it's an expensive technology just to bring the equipment to the site and operate for a few months we're talking about $1 million. So it's not going to be applicable to every site, that's for sure. I think I've taken care of, interesting, this is a conversation that got brought up over lunch, but we were talking about the long-term liability that's retained with just an offsite disposal scenario. We've actually, over my career working in thermal alone, so the last like 16 years, I've had 2 landfill projects where we've come in and actually cleaned up for the responsible parties. Landfills closed. Now, a large RP group gets pulled aside, that whole cradle to grave thing, and they're responsible for the cleanup of some type of municipal landfill. But one of them's operating right now in the Northwest. Kind of interesting that you can't get rid of that liability with a dig and haul scenario. So I mentioned we're going to be talking about a few different thermal technologies. I'm going to spend a lot of time on thermal conduction heating and then electrical resistance heating, because by that far, out of all the thermal technologies, those are the 2 that are used the most for a wide variety of contaminants. So I've got the contaminant like boiling point listed there in the big red arrow. So you see electrical resistance heating applied the most for like a chlorinated solvent scenario, whereas thermal conduction heating, if you're confident that you can remove water from the matrix, you can go to temperatures where you're actually boiling some other interesting contaminants. HEPA remediation down at the bottom is just a brand name that TRS uses. And actually Flex Heater and OptiFlex, that's just TRS's branding of our own version of those technologies. You talk to the other thermal vendors out there and they've got their own little twist on the name as well. But HEPA remediation is like a low temperature strategy. So you just use heat to enhance some naturally occurring processes, such as like hydrolysis of energetic compounds or pesticides. So you're just using heat to speed up that reaction rate, or even heat enhanced by, there's been some cool projects out there, just using temperature and changing the temperature, the ambient temperature of the subsurface to speed things up. And I've lost my timer. It went into sleep mode, but anyways, so steam is another technology. It is far less popular. It doesn't have a chance to be implemented enough. So 16-year thermal career, and I've only ever been involved in 2 steam projects out of that perspective. And you know, I end up touching anywhere between like maybe 3 to 10 thermal projects in a year. So they're just rare. They're gems though. They are awesome. Steam is amazing technology where you can generate really high temperatures quickly, ex situ, of course. You're doing that in a boiler, and then you're pushing that fluid through the subsurface. And the goal of that delivery of steam to the subsurface is to physically displace usually an elm apple that's hanging around the top of the water table and push it towards an extraction point. So these projects, they're not as common. The geology certainly matters significantly. You've got to be very confident that you're going to be able to move that fluid through the subsurface. So you're generally talking about like really highly transmissive aquifers that do have that elm apple element to it. It's not a technology that is applied for DNAPL applications. DNAPL, you know, when you start to change the temperature, you want to be really confident that you'll be able to extract a product in the subsurface. So the lighter, you know, the oils that have the density that favors floating, it's far more commonly used for that type of application. So these are rare. I'm not going to spend any more time on steam, just a heads up. Now I'm going to move into everything ERH and TCH moving forward. So doing that side-by-side comparison, and I see Michael squinting in the background. So hopefully the font size is okay, but I'll try to walk you guys through this here. So I gave you a hint earlier about temperature and the applicability of ERH versus TCH. So that first row is dedicated to the maximum temperature that's, you know, practical in our environment. With ERH, we are relying on the moisture or the water in the subsurface to allow for us to conduct electricity from one electrode to another electrode. So this technology, ERH, is actually self-governing. It will never go beyond the boiling point of water because as soon as the water is gone, it actually stops working. So it just can't physically go beyond the boiling point of water. And what boiling is, we'll get into more details in the future. When the maximum temperature of a matrix that does have moisture or any content of water to it is going to be the boiling point of water until you remove all the moisture from it. At that point, you can climb to temperatures that are beyond the boiling point of water. So TCH, when you remove all the water, you can go to temperatures that are 400 degrees or plus, which is some of the stuff that we're doing on the PFAS front right now. Saturated zone, we already talked about that once we have moisture, any type of water in the matrix, we're never ever going to go beyond the boiling point of water. That's important. No matter what technology is being deployed, you won't be able to do it because moisture, steam, when you're generating that, it actually has a coolness. Well, spacing, so ERH, you can deliver a lot of power quickly to the subsurface using electrodes. So you find those electrodes, Paul was talking about really large diameter boreholes, 12 inches. That's our typical with an electrode when we're building it in the subsurface, a 12-inch or 10-inch casing, if we're using sonic, is our typical. And we are spacing the spacing is pretty far apart in comparison to heaters that we use for TCH. The time to achieve the temperature is really quick in both scenarios. The high power delivery with ERH, if ERH is going to work, and we'll address that later, is going to be a little bit faster of a time that it takes to get to temperature. And then with regards to the vendors, the other thermal vendors in this space, we have a competitor that's been doing ERH for a really long time. And we've got another one who's making their way into the industry right now. TCH, all the thermal vendors. TCH is kind of like an on-off technology. There's a lot of optimization when it comes to ERH and kind of specialized power delivery systems. TCH is a little bit easier to manage during the operations. So you're seeing a lot more thermal vendors enter that space. We talked a little bit about power delivery and some of the advantages that ERH can have if it works in your site setting. So overall, the energy consumed for a project, an ERH project, is a little bit lower in comparison to TCH. Again, we talked about the high temperature applications, though. There's some of these projects you just can't ever get to the temperature that's needed. So TCH is going to be the only technology that works. What it looks like in the subsurface. So there's some type of borehole or heating infrastructure that goes down below, telescopes down below. And we co-locate every single heater or electrode point with some type of vapor extraction, all within the same borehole. So we're collecting the vapors as the subsurface is heating and going all the way up to those steaming conditions that we're talking about. All of those contaminant vapors, steam, get processed using equipment that is mobilized to the site. And again, typically that operation of the system, I described this is almost like an SVE system. It's really on steroids. So it's oversized equipment that is going to operate for just a few months at the site. The actual treatment of the vapors, the liquids, we can sort of plug and play whatever the site needs, but typically we are using granular activated carbon. Sometimes we go through so much of that, we'll actually regenerate our own carbon at the site. We have a few different steam regenerative carbon units, which are pretty powerful little systems. So we do that if we see a lot of mass that we're recovering, or we also use like catalytic oxidizers, thermal oxidizers to do on-site destruction as well. That sort of endpoint depends on just what the contaminant mix is and how much mass we're expecting at the site. So I promised you we would geek out together about boiling, and here we are. So pull up your little blankies and get ready for a nap. What is boiling? So to boil a liquid, you have to have that vapor pressure of the contaminant or of water, of that liquid, equal to the ambient pressure. And we have the ability to change that vapor pressure when we're changing the temperature that liquid is being exposed to, right? So we're dramatically, exponentially increasing the vapor pressure over a really short period of time when we're raising the temperature. So we're forcing boiling to happen real fast. Napples, as I mentioned before, we're going to spend some time talking about denapples in particular. Napples are pretty amazing because when they're present in water or with soil moisture in the vadose, they form what's called a positive heteroazeotrope. So their vapor pressures actually become additive with water, which means they're boiling at lower or depressed temperatures in comparison to just the simple boiling point of water. Why is this important? This is important because before you even get to the boiling point of water, you're actually creating conditions in the subsurface that have boiled off the napple first, which makes thermal really effective at removing that residual napple that's trapped in the subsurface, or horrific pools of napple that you might have. So this stuff isn't exactly intuitive. You could, reference all of this stuff on the internet. Wikipedia, EnviroWiki is a really powerful tool for double checking all this stuff. But that azeotropic boiling point is essentially what we are targeting, and it occurs at a lower temperature than even water. So looking at one really difficult high boiling compound, 1,2-dichlorobenzene. it boils in its pure form inside of the beaker around 179 degrees Celsius. And that, of course, depends on where you are in the world and what kind of elevation above sea level you are at. But let's just say that we're at sea level, 179 degrees Celsius. That it's pure boiling point. When you put 1,2 DCB inside of a beaker with water, which is what we did here in this experiment, it's of course been dyed, so you see that dramatic red color. But we are at a temperature that's just 98 degrees Celsius, and you're starting to see the effects of boiling here with the creation of that steam bubble. This is not boiling of the water itself. So you do not see that rapid boiling effect that the water in the beaker has. Instead, it's just focused on that interface there at a temperature that's a little bit less than the boiling point of water, around 100 degrees Celsius. So 1,2 DCB is a high boiler. PCE boils at a temperature that's around like 87 degrees Celsius, when around water, TCE is even less than that, 73 degrees Celsius. This is a very effective DNAPL, or thermal is a very effective, let's remove the DNAPL quickly, technology. So we see this in some of our site data. This is just simple temperature data that's coming out of a site in New York. So you've got great examples of some sensible heating, which is occurring. So we've got day 1 of operations right here at 0 days down at the bottom. And we've got sensible heating occurring. So we're putting energy in that matrix and we're seeing an effect on the temperature. So you see that temperature rate increase, or the actual measured temperature increase, not the rate. But then after about like 14-ish days, you see latent heating at that blue line. It just like, it's stagnant. It stalls around, let's say 63 degrees Celsius. And the reason for that is down at the bottom of this graph, you've got some details there. This is a DNAPL site. We've got 111 TCA here at 20 feet below grade. So that blue line is measuring the temperature that is right around where that DNAPL is expected. So what you're seeing there is actually the azeotropic boiling point of 111 TCA. And it's not until the DNAPL is removed completely from the subsurface that you're able to see that sensible heating again. So that's when you start to see that temperature change around like 40-ish days. And now it's going up again, and it stalls out again at the boiling point of water. Boiling point of water at 20 feet below grade is a little bit higher than 100 degrees Celsius. That's because you do have some additional pressures from being measured, 10 feet below the water table. So water at this site is about 9 feet below grade. So at 20, you've got a higher boiling point of water. But this is cool stuff. I think this is cool stuff. You guys might all be like, no, Lauren, this is boring. Let's just wrap this up and go home. But there's real site data out there that shows actually DNAPL that is in its boiling form. So another cool thing about thermal is the creation of DOC. There is some humic acids that do break down once we introduce temperature into the equation. So there's some breakdown of some organic matter in the soil, and we're actually creating some dissolved, some DOC with time over thermal. The yellow bars in the back are the starting concentrations before thermal. The red bars in the middle represent how we made decisions to shut the system off. So that was the endpoint of thermal. And then the data that's presented in the foreground, the blue bars, that just represents the data a couple of years later. This is really old data at this point, but this was one of the first projects where we saw this measured effect. This was, TRS was maybe just 6 years out of its creation, and it was like, this is amazing. This is the opposite of rebound, and just trying to wrap our head around it. So you've got the addition of some continual degradation that does happen after thermal. Again, you have to remove that source completely. And then you've got this nice warm environment with a little bit of extra food that's left in the subsurface. You see concentrations of the VOCs continue to decline with time after thermal. We've spent a lot of time today talking about what elements of the conceptual site model are important. We like to take in all the data. When we're evaluating a site, we've got about 80 different parameters that we're looking at. And we'll talk about some of the most important ones in a slide or two, but trying to learn as much as you know about a site quickly and then plug it into our model. We call our model the heat wave model. Some of us at our firm call it the engineering spreadsheet, which the marketing department tells us is not sexy enough. So heat wave model it is. But nonetheless, we're using that model to help determine, all right, which of these three thermal technologies makes the most sense for this site. We're trying to figure out a way, how do we deliver power to the subsurface fast enough, optimizing the energy budget that is going to be consumed over time. So taking a look at some of the key parameters, both on the input side, that first column, and then also some of the parameters, key parameters that are coming out of the model. And this is not comprehensive by any means, just big picture. The ones on the input side that matter the most, all right, we need someone to draw lines for us on a map. So you've got to have a good idea of where do you want that thermal remedy to be implemented. We most often are targeting concentrations, in the ppm range in soil, but we've done some really dramatic, like let's do the whole plume and bring everything down to drinking water MCLs, which is absolutely crazy. So we've got some crazy projects, but someone needs to be responsible enough to draw that area on a map for us. And then we're looking at the geometry of how shallow do you need to heat? Are we going all the way up to the surface? If so, we know we're going to be exposed to a lot of heat losses on the very top of that pancake or cube, as I've got in the top right corner here. So how close to the surface? Do we have natural insulation with the ground surface that we could work with? Or are we going to have to artificially build one at the surface? Do we have a vado zone? Sometimes we're working in wetlands and we have to create an artificial vado zone and actually build out a vapor plenum. So that shallow extent, and then of course how deep we're going, are really key input parameters for us into our model. What the contaminant is, very key. The overall understanding of like how much mass is there does not have to be perfect. We are very comfortable with assumptions. We need to understand, is it 100 pounds of mass that we're targeting? Or is it 10,000 pounds of mass? Because that looks like a different vapor treatment technology in the end. Is it 100,000 pounds of mass? That would be good data to have too. So big general like gut feels is what we're talking about there. And then a good understanding of what's happening with the groundwater. How much heat are we going to lose during one of these remedies as groundwater moves across this target treatment volume? That's something we want to wrap our head around. The output, of course, we've talked already about which technology makes the most sense. Power density, energy density, so how many watts per cubic yard of material that we're treating is going to be really important to us. And then, the difference between power and energy is just the introduction of time. So how much time is necessary to deliver that power and get your project across the finish line with regards to those contamination goals, that builds into the energy density discussion. The spacing of those electrodes or heaters, whatever the technology may end up being, the spacing of our like steam injection wells with regards to the extraction, the groundwater extraction point in a steam enhanced extraction scenario. And then we've talked about vapor treatment quite a bit, but all leading to good, key parameters that are coming out of our model. So let's take a moment to talk about power delivery. I've already mentioned it a few times. This is a really, really important design parameter for TRS and all the other thermal vendors. If you are interacting with one that doesn't want to talk about it, ask more questions for sure. Power density is what determines how you are going to be able to address the known heat losses that your cube of soil is going to be exposed to in the subsurface. So you're going to lose heat to the top, you're going to lose heat to the bottom, the sides, and then of course, groundwater sweeping across that cube of soil, you're going to lose some heat there too. So in order to raise the temperature of that cube, you've got to be able to overcome those losses and then deliver power at a greater rate so that you start to see that rise of the temperature. So this is a key parameter, power delivery, not just on the design side, but also during operation. So on the right-hand side, you're seeing a graph that's just going up and down, up and down. That is actually just documenting power delivery coming from an electrode, and as it is basically being optimized during operation. So you've got to maintain a nice wetted surface with the natural material in the subsurface, and the blue dots represent water delivery that's occurring in order to keep the power delivery high. So power delivery, not just something that you look at the beginning of the project, but power delivery is something that you're constantly trying to optimize throughout the operation, the fast-paced operations of a system like thermal. Now, last bullet here, and I mentioned earlier that if ERH can work, it has amazing power delivery. There are a variety of situations where ERH will not work. So you've got to have a good handle on that. But if ERH works, clients will more often select ERH because the high power delivery, which means overall there's less energy that's being consumed by the project, but that's only if ERH works. So all of my colleagues today talked about bench and pilot studies. And I didn't have a slide about bench and pilot studies, so I threw this one in last minute in the back, but there's not many of these scenarios. There are a few, and I just wanted to inform this crowd about when we might consider a bench study. So talked a lot about how ERH may not work. Well, when it comes to bedrock, we've got to be really confident that we will be able to conduct an electrical current through the rock. And there's not many scenarios like that in the subsurface. So we're looking for some good porous sandstone. We've got bedrock resistivity, electrical resistivity tests that we will run in our lab to confirm, all right, this is a rock that it will work. Let's save some energy. We're feeling confident about this bedrock setting. Let's go ahead and recommend ERH. There are also scenarios, we're working right now on 2 bedrock sites where we are confident ERH will not work and we're in the process of installing one TCH system. In 2026, we'll have another TCH system in place. So taking a look at the bedrock, any type of cores that you've got hanging around your office, we'll take those cores off your hands and we'll do some electrical resistivity testing to confirm if ERH will work. We'll also fine tune some kind of interesting maybe PAHs or some high boiling contaminants. We'll want to fine tune what that expected planned for energy density is. So we will take some soil samples off of your hands for some exceptional contaminants. And then with regards to pilot studies, over my career, I've only seen a small handful of pilot studies. We're never recommending them for VOCs, but when it comes to like heat enhanced bio, We did a pilot study 12 years ago with a project in the Northwest. We did a heat enhanced hydrolysis project. It was massive. It was about 10,000 cubic yards, but the Army Corps did call it a pilot study. So technically that was a pilot study. And then, most recently, a lot of PFAS projects, which we'll talk about later. So diving in a little bit more into ERH, I've got this is where we transition into case studies. So I'll be talking about what I think are interesting, fun case studies where we did use ERH. So this is a very large system. We are looking, this photo vantage point is just a sliver of the 6 treatment areas that are essentially surrounding this photo point. There's 600 electrodes that were installed at this site. Our power control units are called out there, but they're up top here and they're tied to that utility pole. Those are large, like 40-foot long containers that have all of the different buttons that control and help optimize power delivery during these ERH projects. So you're looking at voltages that are being applied to the electrodes, and as those voltages get delivered to the subsurface, you've got an electrical current that flows from one electrode to another electrode and then back to the power control unit. The resistance that is given from that soil as that current passes through is ultimately what is warming the subsurface. So that's how ERH is working in this photograph. And then the majority of the equipment that's actually brought to the site outside of those power control units are all the vapor and liquid treatment stuff. So you're seeing 4 steam condensers all in a line. Again, this is a very massive project. Usually we just have 1 or 2 of these steam condensers. And then you've got our blowers, our vacuum blowers. Very small little gap vessel there. This project also had an RTO system, and you're not even looking at the liquid treatment system. This was a former automotive manufacturing facility. So this was a TCE project, but we had a lot of fuel oil that was also recovered from the subsurface at this site. Another project, this is Joint Base Andrews down in the DC area, where we operated a thermal remediation system. This is ERH again on either side and in between a couple of CSX railroad tracks. This project was really unique because it was a wetland area. So when you're looking at this well field, you're kind of looking at like a cemetery with these bumps. We artificially created a vapor plenum at this site. So we imported gravel to make sure that we had a vadose zone to work with. It's just 6 inches across the site. And then on top of each one of our electrodes, we build it up to a foot, which created that little like cemetery kind of burial ground effect. This site was also unique because instead of just a borehole in the ground for an electrode, we actually put sheet piles into the subsurface and operated sheet piles as an electrode. So sheet piles have, great surface area. And for us, it's all about surface area. This is above bedrock. We love using sheet piles for electrodes. Again, offering a lot of power delivery when it comes to that surface area. So they're really attractive, but for any of our bedrock projects, we're not leading with the sheet pile design. A lot of the data collected at this site, of course, CSX was most concerned about causing all kinds of problems for us during the design phase, but also making sure that their tracks do not move at all during both construction and then the operation of the system. So a lot of great data. This was a in situ application inside of the building with a big bubble over here. Right at the corner of that building in the basement, we actually took apart our equipment, put it into a freight elevator, and then rebuilt it inside of the basement of that building. It's a residential building in New York City, and we also operated some electrodes outside in the sidewalk area as well. all kinds of permitting agencies that were involved there. And with that, I just got a warning.
No, sorry, it's 3:15. I lied.
Oh, okay. Okay.
My brain's off.
I knew I needed a timer.
Dang, that's my fault. No.
All right, bedrock. We've talked about bedrock a lot. This is a really cool project with a 90-foot thick sequence of sandstone that we heated, because sedimentary rock is the rock that we use ERH with, where we were targeting TCE, removing it from a rock. This is the temperature profile. So a lot of data is presented here. Let me try to walk you through it. Up at the top is ground surface. You've got a very shallow overburden, so a little bit less than 20-foot thick overburden, and then the rest of it is the sandstone. Temperature profile over the entire course of operations at this site is presented every 2 weeks, represents a line. So that brown line at the very end is essentially the conclusion of operations. So just wanted to show you this data showing that we can heat all the way up to the boiling point of water using ERH in some bedrock settings. Really important to do that electrical resistivity testing. I'm going to skip ahead here, just making sure that we've got enough time for all of the technologies. So TCH heaters are all the thermal vendors have UL listed type of heaters that they work with. They've all been tested by third parties, rigorous, crazy testing that we've been put through, destructive testing all the way to destroying these heaters. Ours are patented, so we can vary the amount of power that's being delivered at certain intervals across that heater, trying to focus that power to influence the temperatures where we want the temperature to change. The heaters themselves are installed within a casing, and they're operated at several hundreds of degrees Celsius. And then that heat front propagates out from that casing, and it overlaps with nearby heat fronts that are coming from other heaters installed within other casings, all within this small diameter. There's more heaters that are installed at a TCH project in comparison to ERH. So we did talk about how there's a larger diameter that's necessary for electrodes. With TCH, you are able to get away with a smaller diameter, but there's many more boreholes in comparison. So talking about some case studies that we've recently done. This is a big super fun site that we did for a responsible party in Northwest New Jersey. Beautiful area of New Jersey, by the way. Lots and lots of heaters installed here. They were about 230 feet long, one of them, or several of them rather. You'll see we had really complex, highly angled heaters that were installed here. This is the room that we were given access to. And then from this room, we had vertical heaters installed, and then also angled heaters going out to a portion of the manufacturing facility that we did not have access to. So there's a lot of different tools that we can use in our toolbox with regards to access. This is a high angled installation, but we've done a lot of horizontal applications too. So where you could put a drill rig sort of dictates where you can do a thermal project. This is a video of those heaters. This is TCE. Remarkably enough, we were only targeting 300 pounds of TCE in the vadose zone here. So really small amount of contaminant mass. Kind of blows your mind with how much drilling was done to attack 300 pounds of TCE. We always remove more contaminants from the subsurface. We removed over 4 times than what the consultant had expected, but highly angled stuff. Here's the installation. Oh, we have sound. Gonna let me out. Yesterday we did not. But here you can just see the heater itself, that cable contraction, that's the heater. And then you see the casing. It's not your typical monitoring well. It's a watertight casing that's installed into the subsurface, welded. all welded together, but the heater is just sliding in. So this site, we had that area of the facility that we had no access to. It was clean manufacturing operations. So we actually had to bring all of our vapor recovery piping, all of our power cables up onto the roof, and then back of the facility where our equipment was. Here's another application in the Northwest. Here you could see more TCH. You see those boxes just like you saw in the previous one. This is a pretty simple wide open field. You've got nice vertical insulation. We're doing a high temperature, slightly elevated temperature at this site, 2 different phases that we're going to operate the system. We just concluded phase 1. So that's the system that's in the foreground of this photograph. In the background, you see that cover at the surface, and there's not as much stuff that's on top yet. This photograph was taken during construction, but we just turned the second phase of the system on, which is in the background. Something that you could note here is we've got another type of surface material that we're working with. We were treating all the way up to the ground surface, so we've got an insulating cover is what you're seeing there at the surface with aerated concrete. So here's some of the power delivery systems. You saw that really large 40-foot container with ERH with all the bells and whistles included in it. Much smaller delivery with regards to electrical distribution with TCH. Our operators love these TCH systems. There's not as many things that they have to do during operations, so it is pretty simple. It's kind of like a turn the system on and then occasionally reduce power. Here's what some of that infrastructure looks like. I talked about how we do try to co-locate vapor recovery as often as we can. So you're looking at some fiberglass vapor recovery lines that are elevated above the surface. And now switching gears a little bit to talk about my favorite contaminant right now. We've been involved in a few different PFAS projects, which are pretty exciting, bringing this technology to the market for PFAS. So this is a TCH application, high temperature. We're never using ERH for PFAS. You've learned a lot about TCH at this point. Hopefully by now you recognize this. Because it's high temperature, you're not going to be doing this in the saturated zone, right? You've got to be really confident you'll be able to remove the water from that soil. So it's an in situ application in the vadose zone, above the water table, or it's in a soil pile is what we've done so far. So first step with this research was just taking a look at the literature and what it was telling us with regards to these PFAS and the boiling point. So on the right-hand side, you're seeing some of the more common PFAS analytes there, liquid, and then their corresponding boiling point on the scale. All the way far left, you're seeing, I would say, normal thermal remediation contaminants that we're working with is plotted there. So we're working on a project in Puerto Rico right now where dioxin is the main contaminant of concern. We're going at 375 degrees for soil in Puerto Rico. In the Midwest, working on a PCB project. So these are really common contaminants for us, and PFAS certainly well within what we would be comfortable getting to with regards to soil. The next step was some bench testing just to confirm what we were thinking. Multiple different target temperatures that were tested. I've only got select data that's presented there. So lots of testing occurred before 300 degrees Celsius. We were really hoping we'd see some reductions at 100 degrees, 150 degrees. Absolutely nothing significant. 300 degrees was really the first time we saw that reduction. Significant, but not enough. Not what we're used to in the thermal world, right? 99.9% is what's typical for a thermal remediation project. And we really didn't see that until 350 degrees. Once we went to 400 degrees, that was when we got non-detectants. So this was all self-funded research. We published, of course, but it wasn't like actual field work. So we went to ESTCP and submitted some proposals for some field demonstrations. First, we did a really small, only 100 plus, a little bit more cubic yards of soil material in a soil pile that we treated. And then the next project was an in situ application. The first project was in Fairbanks, where we got to measure the highest temperature we've ever measured in soil at that time. We've since gone higher, but it was 437 degrees Celsius, which is really exciting for our company. But the very same day we measured the lowest ambient air temperature that we had ever been exposed to. So some really crazy conditions in Alaska. And then we went to California to do the much coveted, everyone loves going to California, but the much coveted Beale Air Force Base, where we did an in situ project. Another really small volume of material that was targeted at Beale. These two projects quickly turned into another project where we targeted about 2,000 cubic yards of material in a much larger soil pile. This was up at Joint Base Elmendorf-Richardson. We went back to Alaska. That didn't mean that we took our equipment from Fairbanks and moved it to Anchorage. Oh, no, no, no. We moved it all over the place. And then we went back to Alaska. It's never efficient like that. This big gray pile in the center is what represents our soil pile. And then you've got our supporting electrical and treatment equipment there that is also shown in this site layout. So the actual building of this soil pile was very engineered. Our source materials in the background of this photograph, there is 6,000 cubic yards total. The Defense Innovation Unit, this really cool arm of DoD, was hosting a few other technology demonstrations at the same time. So we wanted as much material as you can give us, and we were given 2,000 cubic yards of material. So we moved the soil. You can see one of our operators, actually he's not even in the operator, he's taking, or in the cab, he's taking the photograph, but they're building out this soil pile in individual like lifts. And what you're seeing there horizontally are just the casings. So we're going to be putting our heaters inside of those horizontal casings, all built within that soil pile. Insulation, very important. We talked about it at the surface level with the aerated concrete. At this site, we used rock wool. That's the yellow material that you're seeing there. We also used a base insulating layer where we introduced gravel and then put some heaters inside of that base material to just warm up the surface and prevent the loss to the ground surface with that permafrost. Is how we overcame that. It's a very key design parameter. Starting concentrations in the soil pile were not that significant, not what we consider significant in the thermal world. It was just about 50 micrograms per kilogram of total PFAS. Those are some of the yellow or red areas that you're seeing that soil pile. And it primarily consisted of PFOS, PFOA, and then 8,2-FTS. On the left-hand side, you're seeing a plot of all of our discrete baseline soil sampling locations. There were 30 total within that soil pile, and we did some composite sampling as well. Taking a look at the vapor and the liquid treatment system. So we're coming out of the soil pile over here with a variety of vapor recovery wells. And then this is where it's going from the soil pile. So the very first thing that we do in this scenario is we're cooling the hot gases that are coming out of that soil pile. And so we are converting some of that PFAS mass into the liquid form at that stage, or putting it into water for treatment. For these projects so far, it's been really low mass applications. We're just putting it on carbon for regeneration. That's all that we've done so far. There's so much opportunity to plug in destruction technologies here for like a complete on-site destruction solution. but we just haven't done that in these demonstration projects yet. Lots of data. This is an ESTCP project, so DoD's like grant funding arm for technology demonstration. So they love their data. You've got a temperature plot on the left-hand side, and then just some air data that came out of the soil pile. So this is like influent concentrations. And interesting part about that air data is this is what's measured before quench, just what's in the vapor that's being extracted from that soil pile. But you see all of operations that's plotted there, and you see a really quick drop off of those PFAS concentrations. There's some other data in there like VOCs and SVOCs too, but temperature, just worth pointing out, you guys might expect this at this point. You see that sensible heating and then latent heating again as we try to boil off all the moisture that is a part of that soil. So you see things just hang out around 100 degrees Celsius until we're able to boil off everything. And then you see it skyrocket to 400 degrees and beyond. So just wrapping up here with the results slide for this project. We've got some tough assay data that's presented there up top. This is the baseline data. The post-thermal data is actually not interesting at all because it was just non-detect with the top assay data. But one mention with regards to all of those discrete soil samples that were collected for those individual PFAS analytes, 1633 was analyzed, the laboratory analysis for this data. And it was all non-detect with the exception of 3 analytes that had trace detections. So some pretty cool data that's coming out of these demonstration projects. So I know I said before that there's not many of these field demonstration projects, but certainly right now in the PFAS front, there's a lot of them that are happening. So conclusion slide, which means we are a step closer to wrapping up today's workshop. I think thermal is pretty cool to remove a bunch of mass very quickly. We've got all different kinds of modeling that we're doing to support technology selection, some of those key design parameters that we've discussed, but also just physically the visualization of where those heaters or electrodes went as we're doing the horizontal angled installations. All kinds of R&D. I mean, we do not stop on the research and development front, whether it comes, the majority of our R&D money is spent on power delivery and optimizing our systems, but the latest and greatest you've heard with regards to some of those PFAS projects too, big investment. All kinds of cool applications, in my opinion, in situ, ex situ. And what we're talking to our clients about is actually some hybrid applications, especially in those fire training areas right now, scraping all the superficial soil and then piling it up in a true like PFAS source area is what we're seeing. So with that, maybe there's a couple more minutes left for questions.
Exactly 2 minutes.
2 minutes. Okay. Does anyone have any questions? Yeah.
In all the situations you've had, using available on-site power, you have to generate power yourself.
Okay, that's a great question. The majority of our sites, we are able to get power to the site itself. The one project that I could think of in my history, just to go back to show you how ridiculous this is, I can't help but laugh, but right here. New York City. You would think there would be enough power accessible in New York City, but we actually operated this system, as ridiculous as it was, using generators. So we generated our own power. This was a site highly motivated by a responsible party who was paying hundreds of thousands of dollars to rent out the basement, and they were looking to get rid of the liability. Yeah.
You know, the vapor recovery, using horizontal wells.
So we have, especially when we're working underneath buildings, we will use like horizontal or angled We also we throw a vapor recovery screen inside of one of our electrodes or our heaters, that borehole, then we'll build out a vapor recovery point all within a borehole. Yeah.
So do I understand that you haven't done PFAS destruction?
No, thank you for bringing that up. As you say that, I want to make clear, this is the desorption of PFAS from soil. So just like we would with like a VOC, we are just getting to a point where we're volatilizing. There is transformation, so there is some transformation that we are recording at these sites, but we are not targeting temperatures where we're destroying the compounds in situ or in that soil pile. Yeah, just targeting volatilization.